Marcos Andrade Jr. Marcos is a postdoc at UFSCar. He's also from the DEC program. So Marcos.
Hello, everyone. My name is Marcos Andrade. I'm a postdoctoral researcher at Professor Mascaro's group in Federal University of São Carlos. And today I will present the results we got along the way we took to fabricate highly efficient photoelectrodes for water splitting. So let's get started introducing what's needed for a highly efficient solar-driven water splitting. And the photoelectrochemical water splitting devices are composed by a photocathode and a photonode, which uses the solar energy to convert into hydrogen and oxygen. And today I will focus only on the photocathode fabrication. And for that, it's important to highlight that the multi-junctions designs are more efficient because they can absorb enough solar energy and provide sufficient free energy for water cleavage. However, we need to decrease the cost and complexity associated to the device fabrication. And for a good photocathode, cocatalysts are also very important because they substantially improve the performance of these devices by reducing the activation energy to initiate the hydrogen evolution reaction. They can assist in the electron hole separation at the semiconductor electrolyte interface. And they also connect as a protective layer, avoiding photocorrosion. So regarding the characteristics that we think are important for a good photocathode, I will show you first the investigation that PhD candidate Hugo dos Santos has been doing on the activity of nanostructure copper oxide photocathodes. So cupric oxide nanowires, as we can see here in the scanning electron, cupric oxide nanowires, as we can see here in the scanning electron microscopy image. And further, with electrodeposited the cuprous oxide nanoparticles by electrodeposition, and both copper oxide phases are confirmed by X-ray diffractograms. So the photocathodes of copper oxide nanowires decorated with cuprous oxide presented a higher photocurrent. We notice an increase of almost 0.5 milliamperes per square centimeters. And we believe that the reason is because when we add the nanoparticles of cuprous oxide on the cupric oxide nanowires, we form an heterojection. It brings the minimum of the conduction band closer to the redox potential. And it also can improve the discharge separation, consequently improving the reduction reaction. And it's clear the positive effect of the addition of the cuprous nanoparticle, copper oxide nanoparticles. And in future, we're going to study the effect of the concentration of these nanoparticles on the cupric oxide nanowires film to determine the best conditions for water reduction. So the other kind of photocathodes that we've been investigating, now we're going to show you the results of a very hard team working that the undergrad students Arthur Salomão and Milena Araújo and the PhD candidates Hugo dos Santos and Marina Medina have been doing on the chalcogenides photocathodes. So one of the chalcogenides that we've been studying are the copper gallium sulfoseleenides. These films are deposited by a solution process approach. First, we deposited the compound as a sulfide by spin coating using an ink containing the metal of the salts and thiourea and dimethylformamide. And then the copper gallium sulfide is transformed in the selenide phase by thermal treatment under a selenium vapor atmosphere. So we obtain here a film with 95% of selenium in the composition. We obtain here a compacted film with a thickness of about 0.5 micrometers. And we finished the device by, after that, depositing a buffer layer of about 40 nanometers of cadmium sulfide, and then 100 nanometers of titanium dioxide, which acts as an electron a transport layer and also as a protective layer, increasing the stability of the photocathode. And we finished the fabrication of the device by doing the deposition of platinum as a cocatalyst. These copper gallium sulfoselenide photocathode producing a photocurrent of 1.8 milliampere per square centimeters, which is lower than the values obtained for the ones fabricated by vacuum-based methods on molybdenum substrates. And therefore, we have decided to modify the composition of the copper gallium sulfoselenide in a way to improve the photocathode performance and have results more compared to the literature. So we fabricated copper gallium sulfoselenide now by doping the chalcopyrite with bismuth and antimony. These films were deposited using the same method I have presented before, but now we substituted 0.5% of the gallium by these dopants. So using the antimony and bismuth doped copper gallium sulfoselenide photocathodes, we obtained higher photocurrents and reaching up 11 milliamperes per square centimeters when doping with bismuth. We also noticed the onset potential shifted more positively, and we reached a half cell solar to hydrogen efficiency of almost 2%. With that, we achieved a new photocurrent world record for water reduction reaction using copper gallium sulfoselenide photocathodes. To understand why bismuth and antimony doping promoted the high photocurrents, we plotted the photovoltage that we obtained by JV curves versus the light intensity. We know that the higher the light intensity, the higher is the photovoltage. But because of the larger concentration of defects in copper gallium sulfoselenide, there are these mid-gaps states that become more populated with increase in the light intensity, and makes that not allowing the photovoltage to further increase, and instead cause the quasi-Fermi level pinning. But when we dope in the copper gallium sulfoselenide with bismuth or antimony, we decrease or vanquish these deep defects, and therefore the photovoltage pins more positively, because the difference of the onset potential is exactly the other chalcogenide that we've been studying is the copper zinc tin sulfoselenide, which is also a multi-ternary chalcogenide, and the multi-elemental compounds, they generally have a high concentration of defects. In this case, the defects are due to the copper zinc disordering, because copper zinc ions has the same ionic radii. And to mitigate that, we partially substituted the copper by silver to decrease the disorder, once the silver ionic radius is much larger than the one for copper. As we expected, we obtained a high photocurrent, and the onset potentially shifted more positively as well. In the case of the copper gallium sulfoselenide that I showed before, we proved the presence of defects by plotting the photovoltage versus the light intensity. In that case, we obtained the photovoltage from the JV curves, and for that we need to fabricate the whole device. Here, rather than that, we calculated the photovoltage of the absorber layers by absolute intensity photoluminescence in different light intensities. we use the black body emission to obtain the absolute intensity, and we fitted these curves with this Katahara modified Lorentz equation for a PL emission, considering in this case the semi-band gap states, and then we determine the photovoltage. So by plotting the photovoltage calculated from the PL curves versus the light intensity, we found the conclusions are the same as was obtained before for the copper gallium sulfoselenide photocathodes. We mitigated the concentration of defects. The flat band for the silver substituted the CZTS is more positively, suggesting the annihilation of the detrimental defects. So these results open an opportunity to screen a variety of modifications in the chalcogenide subsoil layers with no need to fabricate the entire device, which is very time consuming. And then we can identify candidates with more potential to be applied to highly efficient photocathodes. So the last results I showed for the chalcogenides were based on photocathodes containing platinum as cocatalysts. Although platinum has presented best efficiency and stability for hydrogen evolution, this element is very expensive, and its scarcity makes it unfeasible for large scale. For that, we need to optimize the photocathode to be platinum free, and with earth abundant and non-toxic elements that can result in low cost of fabrication and more sustainable production of hydrogen from water. So the platinum-free catalyst that we have been investigating is the moly-sulfide. We have studied the best parameters to deposit the molybdenum sulfide on the CZTS photocathodes with this configuration. For that, we used a solution of ammonium tetrathiomolybdate, and we applied the potential in this range, obtaining the best results for the water reduction when we prepare the photocathodes, applying minus 0.5 potential. Furthermore, we investigate the effect of the amount of molybdenum sulfide deposited by changing the deposition charge density, and we obtained the best results for water reduction when we deposited the 45 millicoulombs per square centimeters. When we used high charge densities, we noticed this decrease of the photocurrent. It can be associated with deposition of a thicker molybdenum sulfide layer that can cause the decrease of the absorption. Although the photocurrents report in the literature for the copper zinc tin sulfoselenide photocathodes containing moly sulfide as a co-catalyst are higher than the ones that we reached, our results are very promising because we fabricated our photocathodes using an inexpensive substrate in comparison with the molybdenum soda-lime glass. We also investigated the effect of an additional metallic catalyst after the moly sulfide deposition. We deposited a very small amount of platinum. You can see that we use only a charge of 5 millicoulombs in 2 seconds deposition. Here, showing the results for platinum as a control to compare with all the metals, and we reached a photocurrent of 13 milliampere per square centimeters. The nickel didn't act as a good co-catalyst for water splitting, but here we use it as a proof of concept to soon evaluate other metal alloys with nickel, which are very known as good electrocatalysts for hydrogen evolution reaction. So we know that there's still a long way to go, but with the results that are very promising, very interesting results that I just have presented, we believe that we've been advancing to the right way. And thank you everyone for your attention.
Thank you, Marcos. Excellent work. Have you tried another kind of catalyst? Because I think what is very interesting is actually the growing these nanowires. And I had a quick question and also about the stability.
Considering the increasing of 0.5 milliampere per square centimeter, we don't. It's hard to assume that's a huge increase. That is but these photocathodes is still under investigations. Ugu is the PhD student in the group that been fabricating these photocathodes. The results are very similar to the ones that have been reported in the literature, but we needed, yes, you sure we needed to study a little bit more to understand how can we prove these results. And I'm not sure that if Ugu have been doing yet the stability test, so I can answer now, but I can ask Ugu to reply in the chat if he's here, and we can know about the stability of these photocathodes.
Instead of a question, I would like to make a comment. I think it'd be very interesting, Lucia, to test these photocathodes also for CO2 photo reduction.
Yes.
I'd like to see some results on that.
Yeah, this work is in progress, and I think that the other postdoc in the group, Juliana, and the other people will be presenting the results very soon.
Okay, thank you, Marcos.
Thank you. Thank you all.